Okay, welcome back. So we will look at this example how this PLA implement the logic or how we actually program the PLA. So we will, if we look at this F1, we can see that uh, this wire program or we call it connected, right? This one is not connected. Okay, so means that F1 is actually equal to if you look at this is P3, this is P2, this is P1, means that X1 is P1 and this is OR gate. So we represent OR with plus sign, yeah, or P2 or P3, right? And we know that P1 is actually this, which is N, yeah, means that P1 is, yeah, look at the connection. So it should be X1. So P1 is actually X1. This is N. So N is represented by dot like this. And this one is X2. P2 is this, which is X1 and X3, not X3, yeah, or X3 bar. X1, X3 bar, right? And P3 is not X1, and this one is not X2, and this one is X3, right? So meaning that F1 is actually this, X1 and X2, or X1 and not X3, or X1 not X1 and not X2 and X3. All right, so we can call it sum of product, right? So this is F1. What about F2? Same thing. And we can implement another or any other function, right, by just changing the connection here and here. So we can get other logic implementation. So that is mean by programmable in this case. We call it programmable connection, and this is called PLA. So we will use the computer to design the circuit. For example, we want F to be equal to X 1 or X2, all right, or X2. So the computer will generate, because this one is hardware, yeah. So you have the computer, this is your PC, and you will have the cable, the wire that connected to the hardware. This is hardware, all right, and of course this is run by software, right? So it will generate the connection, all right, in the software, and we use what we call the programmer to do the connection, all right, to disconnect and connect, yeah, right? So all this thing is done by computer. We just give the equation, so the computer will give you the connection, the correct connection, all right? So that is mean by programming, hardware programming in this case. Okay, so you can have any uh, function that you want to implement, all right? So that is a PLA, programmable logic array. But when we look at this, yeah, because we have too many connection, and the drawback with the connection, physical connection, mechanical connection is like this, switches, it will reduce the speed of the circuit, all right, uh, of your circuit. So you have switches here, many switches here, also you have many switches here. So there will be a delay, yeah, for signal to travel from here and across the switch, mechanical switch here. And again, to manufacture the switch is not that easy, yeah, difficult. So that is the drawback of PLA. So with that, yeah, uh, there is there was PLA introduced later on, to reduce the or to improve the performance of PLA. So we have PAL, or programmable array logic, all right, where instead of we have OR plane and AND plane, now this OR is fixed. Fixed means that we don't have switches here, all right, we only have switches at the AND plane. And this means connection, connection. So for example, F1 here is equal to P1 or P2 always, yeah, always. So if you don't want P2, make it 0, because this is OR, so we will have only P1, all right. So in this case, F1 is equal to P1 or P2, and P1 is actually this, yeah, which is x1, this is n, right? So x2, x3 bar, x2, x3 bar. P2 is x1 bar, x2, and x3, like that. Okay, so here we can see that we reduce the switches, so we improve at least the speed, and make it more easier to design also, because we will concentrate on the end plane only. Right, we reduce the delay here at the end plane, so that is called the PAL, or programmable array logic, to improve the performance of the previous PLA. All right, next we go to the programming. So yes, just like I discussed or show you before, we will this was the previous, the old technology, where the way that we used to program the PLD, where you need to unplug the chip, all right, put in the what we call the programming unit or programmer here. I put it here, we program, and this one of course connected to the computer, all right, send the necessary signal to make the connection on your PLD device, plug here and unplug and put in the board, in the circuit board, right? So this is how we plug in the circuit board, yeah. And so that is the old way. And then uh, the latest, the one that we have nowadays is called in circuit programming, like this, means that we can program without plug in and plug out the device. The device is on the printed board, all right, fixed already, soldered. Okay, because most of the time we use the IC that is this package, QFP, quad flat pack, which is the pin, where the pin is very small, and it is fixed on the printed circuit board in the factory, actually soldered not by human but by robot, so here we have the connection, that we can connect the USB cable nowadays to the board, and we can program that device directly from the computer, no need a programmer. That is called the in-circuit programming. Yeah, nowadays we use that. So the later, the more advanced technology is this. We call it complex PLD, complex programmable logic device, which is a bigger version of the PLD, or either PLA or PAL. So yeah, the name is complex, means that you have more circuit block. So this is the view of the CPLD, where you have many PAL light block connection together, means that you can create a more complicated circuit using CPLD, because you have more logic block available, right? So this is what is inside the CPLD. Actually, this is the PAL light block. So this is PAL actually. So we see this is PAL, and this is the output pin. And the latest one that is very popular today is this FPGA. All right, field programmable gate array. Yeah, where this is very popular today. Which is used in designing prototype, or very fast design that we can test very quickly. And this is good because from the specification to design to the real to the market, so we need the time is fast. We call it time to market. All right, so we need to a very short time to market. So FPGA is the answer. From specification, we can design very quickly using the hardware description language and so on, and we can implement very fast. Means that we use the FPGA to test our design, right? So FPGA is a little bit different from the previous PLD in terms of how it's implement the logic. All right, it is not using the AND or OR plane. All right, instead it's been used what we call a lookup table, or LUT in short. So this is how we implement logic in FPGA. We use the lookup table, and lookup table looks like this. Means that you have what it is. This is multiplexer, and this is the cell. Yeah, the storage that we can program whether we want to have 0 or 1. We can change this configuration, and we have the output. All right, so this is the two input LUT, right? X1, X2, and this is the output. So for example, if we want to implement this function, this is the truth table, and this is the Boolean equation, and this is function for uh, XNOR gate, right? This is XNOR behavior, where when we have 0 0 at input, we have 1 at output, and if 0 1 or 1 0, we have 0 0, 1 1 1. In other words, if the input is the same, the logic is 1. If not the same, the output is 0. So that is the behavior of XNOR. All right, if XOR is complement to this, right? 0 1 1 0, that is XOR. This is XNOR. So how we implement XNOR in lookup table or FPGA? All right, so what we do is that this. Sorry. Okay, here, right? So we want to implement XNOR. So this is the output. So means that we have the output here, 1 0 0 1. We put this value in this storage. That means that we program. The output must be this 1001. All right, according to this truth table. So if x1 is equal to 0, x2 equal to 0, means that this one is 0, this one is 0. And what is f? So we should get 1 at f, yeah? But how to get that? So it depends on this multiplexer. So if this is 0, means that this line should be 0. This is 0, this one should be 0, this one should be 0. Right? Because this is the same node, yeah? Same node, same wire. So if this one is 0, the output here from this multiplexer should be 0. All right. So this is 2 to 1 multiplexer. Okay, we will learn in detail the multiplexer, how to design multiplexer, but the operation is like this. If this is 0, means that, you see, this is 1, this is 0, means that if this control signal is 0, means that the output from this multiplexer should be from this. If this one is 1, the output from this multiplexer should be from this line. In this case, we have 0, so the output should be 0 here. So this should be 0. And also this one, if this one is 0, the output here should be 1. All right, so we have 0 and 1 here. And here again, look at the control, 0, so should be from this line, go to the output. So 1 here will go to the output, which is 1, correct? Number 1. And let's, for example, the input is 0, 1 like this. X1 is 0, X2 is 1, right? And what is the output? We expect the output should be 0, right? So the output should be 0. And let's see whether the output is 0 or not if x1 equal to 0 and x2 equal to 1. So here must be 1, right? Here must be 1 and here must be 0. Okay, here 1, 1 and here 0. And if this is 1, so what is the output here? Should be 1. Okay, I use the color. Should be 1 here. The output here should be 1. And if this is 1, the output here should be 0. And because this is 0, the output here should be from this line. 0, 0. So we have, yes, exactly 0. And when you change the input to 1, 0, and you will get 0 also. 1, 1, you will have 1. So this configuration, all right, if you have this, you will have the XNOR operation. And if you want to change to implement, for example, AND gate, AND, where the output F1 should be like this, right? AND operation. So what you need to do is just change this to 0, 0, 0, 1. Then you will have the AND gate. Right? That is how FPGA work. All right. So to implement AND, it just need to program this storage. Yeah. Okay. Right. Straightforward. And this is a 2 to 1. If you have a how many here? 3. All right, 3 input. So you will need to have 8, yeah, 8 storage cell in your LUT, and the connection is like this. And you can try, right, every combination to get F, yeah. So 3, of course, you need to have 8 output, 8 possible output. If you have 2, you have 4 possible output. This is normal. If you have 4, all right, so you need to have 2 power by 4, you have 16 output, right? If you have 5, you have 32, and so on, right? So this is the example of what is inside FPGA. So you have many, this is one LUT, yeah, so you have many actually, right? The programming of the FPGA is the same as CPLD, where we use the ISP, or in system programming or in circuit programming. Yeah, the one that I explained before, this one. Okay, same thing. The important thing to note is that the LUT in the FPGA are volatile. Means that just like ROM, means that the value here that we program here, when we off the supply, we will lose this value. Means that if we want to use, we need to program the FPGA every time. Okay, so but nowadays the FPGA got RAM. Sorry, just now I said FPGA is just like ROM. No, just like RAM. Where we will lose the information when we switch off the supply. But nowadays, FPGA has ROM built in, where all the program is kept in the ROM, where you can switch off the supply without losing the programming information. When you power up, it will automatically program your FPGA. Means that no need to reprogram manually, right? So that is the modern FPGA, right? Explain here, so you can read. So what is the difference between CPLD and FPGA? Of course, CPLD is not very large. It cannot design a very big circuit, but FPGA nowadays you can have from about 1,000 to more than million equivalent logic gate, and even billion. Nowadays you can check on the internet that FPGA now has more than billion logic in the chip, right? So we can actually build or design a very complicated, very complex, very big circuit on FPGA. Okay, this is the flow that we will you will need to follow in this course. So first is we from the what we call the design entry, where we can start from schematic and HDL. So in this course, we're not using schematic. We're not drawing the gate, we're not drawing the module, but we use hardware description language. All right. I mean in computer, but in theory, we still need to draw the gate. Yeah. All right. But in computer, we use HDL. We will do the what we call the functional simulation, see whether our design is function, at least in terms of functionality, is okay before we continue to synthesis. So synthesis means that to translate from language to the circuit, netlist to the circuit, and implement on the real hardware and do the timing simulation, whether it's meet the timing or not. If not, we need to go back and do the design again before we download to the real chip. But this one we will not do in this course because we cannot access to the FPGA board for now. All right, so this is the detailed design flow. detailed design flow. So we say this is actually pretty much the same with this one, but more on the flowchart view, or easier to understand. The product requirement, design specification, initial design, we simulate, design correct. If not correct, we need to go back to redesign, do the prototype, testing, meet specification. If no, need to go back. If the correction need to be major correction, need to go back even further, all right, before we finish the product. Okay, so this is the end of this chapter already. Yeah, we in the good progress. We managed to finish chapter 1 by today. So next week we can start with chapter 2. So as a conclusion, uh, before we end chapter 1, so we can see that this is what we can say about this, what we have learned. So few engineers will design custom chip. Yeah, so custom chip, just like I said, this is the final product already. When we confident already that the product is good, so we will create the final design or final chip, IC. So but this is done by very few engineers in the factory only. Some engineer will design ASIC. ASIC, I haven't explained what is ASIC. ASIC is actually is like semi-custom also. Yeah, where we application specific IC. Where this is actually a custom design also. Yeah, these two are custom design. So same thing. But many engineer will design FPGA system. All right, because this is accessible, where anyone in the world with the software, and the FPGA chip is very is affordable. You can buy from the market and test your design straight away. All right, so this one is done by many engineer in the world, all right, in design, right? So in this course we will focus on this one. This one, yes, of course you will learn also if you choose the electronic elective, yeah, electronic or computer engineering elective. So we will learn how to design the actual chip, actual IC. All right. Okay, so that will end chapter 1. So thank you very much. Any question you can ask now, or you can ask through any communication channel that we have. Okay, hopefully this is the introduction that open your eye, that um, explain to you why digital design, why digital system is important, why we need to learn this, and why is it important for you to become an electronic engineer in the future.